Hi, this is Ms. Warnow. We're going to continue working some stoichiometry problems, bringing in all of your previous units as well. So this says, how many moles of aluminum oxides, this is what you're looking for, will be produced if 2.5 moles of aluminum are combusted with oxygen? So the most important, or the first step you need to do, is balance your equation. So in this case, you need to first write your equation. So we have aluminum combusted with oxygen. You have to remember that oxygen is diatomic. Right? So this is going to be a synthesis reaction, and aluminum oxide is Al2O3. So now that we have our reactants and the products, we now need to balance them. So when I look at this, I see oxygen, there's 2 on the reactant, 3 on the product, so I would look at a common multiple. And so the common multiple is 6, so I'd put a 3 here, I'd put a 2 here, and then for aluminum, I'd put a 4 here. So now I have my balanced equation. So if you didn't do well on the reaction unit on writing these in nomenclature, you need to go back and brush up on this so that you can get the reaction correct. All right, so let's begin. We're going to start by, after we balance our equation, by writing down our given of 2.5 moles of aluminum. It doesn't mention the value of oxygen. We can consume oxygen, that there's plenty of oxygen, that is what we call an excess. So we just need to worry about the amount of aluminum we have. So whatever unit's up top comes down the bottom. We're trying to get to aluminum oxide. And where do we find our mole ratio? Is still from the balanced equation. So what's in front of aluminum oxide is a 2. What's in front of aluminum is a 4. These cross out, and we're left with moles of aluminum oxide, which is what we want. So when we go to work this, we should get 1.3 moles of aluminum oxide. Notice that I did pay attention to significant digits, that I wrote the substance and the unit. Let me check and make sure I did that correctly. Yeah, so you see it all pretty there. The heart of it is the mole ratio. For the next one, says how many particles of oxygen gas will be produced as 5.45 grams of potassium chlorate are decomposed. So this is a decomposition into potassium chloride and oxygen. So in this case, they actually told us what our reaction and what everything is. So we have potassium chlorate. It's going to decompose into potassium chloride and oxygen. Remember, oxygen is diatomic. And so then we need to balance this. So I would use the method I did before. Common multiple with the oxygen between 3 and 2 is 6. So I'm going to put a 2 here to make there be 2 oxygen. 2 times 3 is 6 oxygen. So I'll put a 3 here. And then now we need to put a 2 here. All right, so now the most important step, or the first step, is to have a balanced equation. We have that. So now we begin solving a problem. So we have 5.45 grams of potassium chlorate, and whatever unit's up top comes down on bottom. If you're not in moles, you need to get to moles. That's what I'm going to do here. And the relationship is that 1 mole is equal to the molar mass, and the molar mass of potassium chlorate is 122.5. Now if we stop here, answer would be moles of potassium chlorate, but we want oxygen, so we have to keep going. Whatever unit's up top comes down on the bottom. And now that we're in moles of potassium chlorate, we can go to moles of what we're looking for, which is moles of oxygen. And this is our mole ratio, and so we get our mole ratio from the balanced equation. We have a 2 here. In front of oxygen, we have a 3. If we stopped here, our answer would be in moles of oxygen, but we want particles of oxygen, so we'd have to draw brackets again. Whatever unit's up top comes down on bottom. And now we can go to particles of oxygen. And that relationship is 1 mole equals 6.02 times 10 to the 23rd. Now if we stop here, our answer would be in particles of oxygen, which is what we want, so we can do equals. And then multiply everything across the top. As a reminder, the way that you punch in 6.02 times 10 to the 23rd is you do 6.02 EE 23. And then when you solve for that, you get 4.02 times 10 to the 22 particles of oxygen. Yes, I did pay attention to significant digits. There are three. There should be three in your answer. I do have the part of the problem, which is the mole ratio. And I wrote the unit, the substance, and I wrote the unit and the substance each time all along the way. And that's what you should do for each problem. The next one is referring to that same problem. So I went ahead and have this problem, the reaction already set up for you. So it says how many liters of oxygen gas would we produce if 7.2 times 10^24 formula units of potassium chloride are used. So we'll start by writing down 7.2 times 10 to the 24 formula units of KClO3. And then whatever units up top comes down on bottom. Not in moles, get to moles. We'll get to moles. 1 mole is equal to 6.02 times 10 to the 23rd formula units. That crosses out. If we stopped here, our answer would be in moles of potassium chloride. Well, but we want to be in oxygen, so we need to do our mole ratio. So moles of KClO3 becoming moles of oxygen. And then we find this from a balanced equation. There's a 3 in front of oxygen, and there's a 2 in front of KClO. Now, if we stopped here, our answer would be in moles of oxygen, but we want liters of oxygen. So we need to come back here, and whatever units up top comes out the bottom. And then we can get a liters or 2, and we'll assume at STP, we'll include that 1 mole is equal to 22.4 liters. Okay, so when you multiply everything across the top, 7.2 times 10 to the 24, remember you enter that in by doing 7.2 EE 24 times 1 times 3 times 22.4 divided by everything on the bottom. Then you will get an answer of with significant digits. I think with significant digits going to be 4.0 times 10 to the 2 liters of oxygen. I want to say you get something like 4.01.7, something like that. But you only need 2 significant digits. So if you write it in significant digits, you get your 2. You can write out your 2 significant digits in that way. Okay. You could have also done, we also take it like this. We just put the bar right. We'll take that as well. Okay. All right. So what mass of iron 2 chloride is produced when 6.7 grams of iron is dissolved in excess hydrochloric acid? So we need to write our equation. So we have iron. I don't like the word dissolved here because technically it's not going to be dissolved. It's a chemical reaction. Let's just say iron is put in excess hydrochloric acid. So we know this reaction takes place, but you could look at your activity series to see that iron is more reactive than hydrogen, so it will displace it. This is a single replacement reaction. We're going to get iron chloride, iron 2 chloride, and then of course the hydrogen comes off as a gas. But remember that it's diatomic, so you have to put that 2 there. And then we have to make sure we balance this, so it's balanced when you do that. Put a 2 there. And remember, there's always understood ones as a coefficient everywhere else. All right, so let's begin by see what mass of iron chloride. We're starting out with 6.57 grams of iron. So we'll start with 6.57 grams of iron. And whatever units up top comes down on the bottom. If you're not in moles, get to moles. And 1 mole is going to be equal to 55.85 grams of iron. We get that from the periodic table that you should have out. If we stopped here, our answer would be moles, but we want iron 2 chloride, so we have to keep going. And what's in front of iron is a 1, and what's in front of iron 2 chloride, it looks like that's a 1 as well. If we stopped here, our answer would be moles of iron 2 chloride, but we want the mass, so we keep going. Whatever units up top comes down on bottom. 1 mole of nitric chloride is 126.75. So I multiply all of that out together and divide by the bottom. Let's cross this out. We end up with 14.9 grams of FeCl2 is the answer. I'll pull this little tab out to make sure. Oh, I did it right. Okay for me. And there's your mole ratio. If you skip the mole ratio part, you've lost like most of the problems. Alright, so this is a continuation of that one, so I left the equation up. How many liters of hydrogen gas are produced with 1.4 times 10 to the 25th atoms? So, of iron. So we'll start by writing down 1.4 times 10 to the 25th atoms of iron. If you're not in moles, get to moles. So atoms of Fe, moles of Fe, 1 mole equals 6.02 times 10 to the 23rd atoms of Fe. That's old stuff. But if we stopped here, our answer would be moles. We want to be in hydrogen, so we're going to have to do a mole ratio. This is the only new step we have, is what I'm doing right now. And we get that from a balanced equation. 1 mole of iron is gives you 1 mole of H2. Cross this out. All right. And then we would stop. If we did, we'd be moles of hydrogen, but we want liters, so we have to keep going. And what I'm doing right now, this step, is also old. We have converted between moles and liters. So 1 mole equals 22.4 liters. Cross that out. And of course, this should have been, we'll make sure we put this at STP. You can assume in this unit it's at STP unless otherwise stated. All right, so when you multiply everything across the top and divide it by everything across the bottom, you should get 520 liters of hydrogen as your answer. Yes, I did pay attention to significant digits. And I'll have my mole ratio. This concludes video 3 on stoichiometry. You should have taken high quality and in-depth notes with examples, rewatch the videos in need, and ask questions.